Yeah, my background is in mathematics and computer science, and it's right, as you mentioned in the discussion, I really much enjoy working with the life science companies as a consultant in projects where we change the status quo of how to work with data. So this talk is about reinventing laboratory data to be bigger, smarter, and faster. And I assume that this is a goal we can all agree on. So the question is, how do we do this? And my understanding, or my personal, from the experience, is that the solution to that lies in the data itself. It's not necessarily of the processes and how you process the data, but it's treating data as a first-class citizen. Yeah? That's a mind shift. Yeah? You need to think globally, or for your enterprise, what is an experiment? Yeah? What is the essential metadata that we need to capture for an experiment so that then, in the end, our processing and our processes with sample preparation, testing, and all this, in the end, drawing PowerPoint slides, said that we can make this connection and that we are able to link and track things. So the question on how we do this links to the question of what is your data strategy? Yeah. Do you treat data as a first-class citizen? Yeah. When we see how people treat data in the enterprise, then we see that people throw data over a fence. Yeah. From one department to the other department to the another department. Yeah. Export, import. Losing the connections, losing the understanding of how that data was captured, what the structure was of the data, and in the end, from the enterprise perspective, with the helicopter, you have no clue of what this data is all about. So the question is, what is the right strategy to capture or to deal with data? In the past years, people were saying, okay, data is important, we put everything in a data warehouse. Fairly well organized, everything neat together in good structure, tables, columns, everything there in place. We can analyze this. We can optimize the data warehouse to run analytics to answer specific questions. Yeah? You need to have the question in mind when you build your data warehouse. When you have a new question, you probably need to add new data. Again, extract, transform, load from a new data source. Again, you need to build new links. You need to change your data processing pipeline. This costs a lot of money and is error-prone also. And it doesn't scale to the data that you currently see when you look at your laboratory, where you have the multiple devices with sensor data and so on. So what do people do when they are stuck with one solution? Yeah? They see, we cannot go this, we cannot scale this. Yeah? They're in this direction, in this solution here. They go the other direction, to the other end of the spectrum. No transformation. Everything just dumping in somewhere. No cost to transform. Everything there. We can access everything. And we think that both solutions are on the two ends of a spectrum. Maybe it's a bit simplified, but the solution to answer your business question is somewhere in the middle. You won't achieve everything with a data lake. You won't achieve everything with a data warehouse. You need to look at data differently and look and find the proper place in between here. So why is that? Data continues to rapidly change and grow. Yeah, we We have sensor data. We have new instruments. We have big data, and this is already over the past years, and there's huge success on dealing with big data. Data warehouses exist. Every company has one, and they are there. The problem here is that it really requires a lot of effort for limited gains. Predefined questions can be answered. With data lakes, we have this rising trend where we can hold all types of data, from unstructured to very structured data. So images, text, put everything in. Don't control who puts in what. Just dump everything in. Everything is there. And at no cost except the storage. No cost in transforming the data. What you lose is the schema. And so the approach there is that they say schema on retrieval. Yeah? You think about the schema when you actually want to access the data. Yeah? And then a third item here is the graph technology. And graph technology, there the focus is really on linking data. Why is the web so successful? Because we can link documents. Yeah. Here the idea is to link individual data items, to link single pieces of information to capture the knowledge explicitly in the data. And things like taxonomies, ontologies, controlled vocabularies are here. And it's a very flexible schema. It's not a predefined table thing. Okay. So let's get back to the 4 V's of big data. On the one hand, we have the volume, which is the sheer amount of data. And here, this is the typical focus of Amazon solutions and so on. And then you have velocity, which is data in motion. There, the processing of data is important, or the performance to capture data and to tackle the speed of sensor data that is coming to you. You need to quickly decide on what to store actually, or what you need to forget. Yeah? Then you have variety, which is about data in different forms. And here the complexity shows off. Yeah? Consider your lab environments. You have machines from different vendors. They will all give you your data for the same type of experiment in another format. And this is just one aspect of the variety. And then you have veracity, which is uncertainty. And so while the first 2 V's are fairly well solved, semantic technologies are used for tackling the variety, and you need to have statistics or mathematical clustering algorithms to work on the veracity. And that's what we focus on at Oslos. If you look at the laboratory data, you see all these 4 V's. Yeah? You see the volume, I think that's clear. You see the velocity, if I talk about sensor data or measurements taken every millisecond. You see the variety, as I said, with the different types of techniques that you employ, the different setups of your experiments. Yeah? You have these parameters that you need to capture also to be able to interpret results in the end. And then you have the uncertainty that is inherently in your data. When you measure, there's error. Yeah? So you need to be able to handle uncertainty. So how does a typical lab environment regarding data looks like? Yeah? As I said, you have these silos of different systems. So what you do, you have one ELN here, but for the enterprise, you need to look across this one ELN. And a typical, not data science, but a typical or average scientist desktop looks like this, that they have a lot of Excel sheets, for example, from CROs that report on clinical trials. We did a project with people in the pharmacokinetics domain where they analyzed blood coagulation, and they have quite good simulations for that because they don't want to do everything with experiments. They have mathematical simulations in MATLAB or within their own environments, processing machines. But they need to actually make the comparison between their simulation data and actual experiments to train the simulations or make the simulations better, to verify the study data, but they cannot tackle the data that is submitted to them. So they need to feed in the data from the clinical trial to the parameters of the simulation. And that takes them from a day to a month just to run one simulation or make this comparison. And then the results are captured in PowerPoint, also not very good. Yeah. So you have this data silos, and the knowledge is in the head of your SME. We had this just in the discussion here, the common vision between the business units and the scientists. This is missing. Okay. So why are data lakes so popular? The first thing is that they tackle very well the first and the second item of or even the third item. They tackle also the variety. You can store every type of data in every format, yeah, and this aspect of the variety. Yeah? And they use cloud technologies for scalability. And you can maintain your raw data also. Yeah? So what's the problem? Yeah? Data scientists supposed to be the most sexiest job in the world in the 21st century. Yeah? But it's not if you have to clean up a data swamp. And that's what the people are working on. Yeah? Putting everything in, but getting nothing out. They're spending 80% or more of their time on this issue. And these people are highly paid. And you don't have many of them. Yeah? Do you want them to work in this kind of environment? Or should they better work on algorithms and analytics things? Yeah? So the problem with data lakes is that you lose any meaning of the data when you just dump it. Yeah? So at Osthus, we think of lab data science as big analysis. The focus is on analysis of the data and helping the data science people to work efficiently with the data. And there are two aspects, basically. On the one hand, you have the statistical, and the other hand, you have semantic approaches. One is good for trends and analytics, learning things, and the other thing is good to capture your understanding of the world. So it's about a priori and a posteriori knowledge. Yeah? It's about conceptualizations and computation. It's about data-driven versus logic-driven. And in this interplay, the interesting challenges come up. Yeah? And this is not a solved problem. Yeah? So how do you bring these two worlds together? Yeah? How can you build systems that are capable to run all this? Yeah? So data science, and also I think I've gone through that. It's more than just statistics. It's both semantics and statistics. And so one thing, if we start a project with a customer, is always that we look at the semantic spectrum. A key thing, if you look at semantics, is that everybody does this already. It's nothing new. Yeah? You can go to any company. They have their code lists. At least they have country codes. Then they have currency codes. They have their codes for compounds. They have the codes for plants. They have the compounds for anything. Yeah? And this is here on the lower spectrum. Yeah? This lists. And this is already good because lists and code lists allow you that different applications use the same identifier to name the same things. Yeah? But you often need more. Yeah? For example, regulatory submissions are submitted in a dossier where you organize information according to a document structure given by an authority. Yeah? That's in an informal hierarchy, or we call it a weak taxonomy. It's meant to organize information. Then you have the Thesauri, where you're talking about terms and synonyms, abbreviations. You say, okay, this is a broader term. Finger is a broader term than thumb, and hand is even broader. And you talk of these things and how they are related. So you have also, this is related to that, and so you have this kind of simple semantic network. But you don't enforce any logical constraints on this. So what you then cross is the boundary to get a more restricted model. You talk about taxonomies, fairly common in the natural science. In biology, you have this, the International Classification of Diseases is an example. And then you go up the spectrum to conceptual models or ontologies, where you even have more expressive, let's say, language to express your model. And it's not about, maybe the arrow is even not a good icon there. It's not about you need to go there. That's not what I want to say. It's you need to think about which kind of semantics or which level of expressivity do I need to solve a certain business case. And thesauri are fairly enough to use semantic search. Yeah? There you just need terms, synonyms, and so on. That's totally enough. But if you want to do reasoning, then you be more restrictive and more consistent in your models. So as an example where we employ this is Allotrope Foundation. We are here the framework architect for the Allotrope data format. And essentially, the whole thing consists of these three major parts. On the one hand, on the bottom, we have the allotrope ontologies, where we define the different classes and properties. Then you have instance data. This is classified by the ontologies. And then you have data shapes or the data models, which are basically patterns that describe how your data is structured, the data model. And this connection, this separation is essential so that you can combine or that you can exchange also. Because the instance data, for example, you won't share. Yeah? But the ontologies that we develop in the Allotrope Foundation, they are built together with the different consortium members. And by doing this in a collaborative effort, these models are far more robust than if you would do this on your own. And they are far more, let's say, usable in different scenarios. And the approach, maybe it's important, is that we do the whole modeling, that we don't build one big ontology or so, but we do this in a fairly modularized way. So we have, firstly, at the very basis, we have taxonomies for instruments, processes, materials, and results. And then we have these cross-hierarchical links to form really ontologies that make this. So when I look at the enterprise applications or the overall architecture, we see that we cannot go with just one solution or with one type of solution. We have hybrid architectures. You think about your instrument data, document stores, cloud databases. Many companies started to have their private Amazon cloud. They see that, okay, for this, Amazon is really good. We want to use this technology. Structured databases there, all your old relational databases reside. Then you experiment with semantic databases. We have a customer that has about 2 billion triples that represent information about phenotyping and links this to common reference data. So having this different, I think all of you have this kind of things, and you have even more things. And what you also want is to include public data. Why do you have to generate all the data on your own? In Europe, there's this Horizon 2020, and they now require that everything that is funded and all the results should be published also, and make publicly available. So you want to gain from this. You want to reuse publicly available data, and then you have this dashboarding analytics things. What our understanding is, and we see this in projects we're doing, is that we need a lightweight semantic integration layer in the middle to make the application speak the same language. And the emphasis here is also on lightweight. It's not necessarily that you have to build your enterprise ontology. That's not what we are talking about. It's to, in the first place, harmonize your reference master data. Harmonize your code list. Do this in a state-of-the-art way. Don't you let applications define their own vocabulary that is not mapped, not aligned with other vocabularies with the same coverage. Yeah? Why does every application has to have its own list of country codes? Yeah? Some refer to the ISO codes, others refer to their internal code list. Why can't you just use one methodology to store this data? And then you have the marketing department. They have regions on Earth which they link to the countries. You have regulatory regions, where you have an authority behind that says, if you register here, your product is valid in these countries. Why not have this in one graph, in one reference data graph that you can then use to express your data and allow applications to talk the same language? And we implement this with clients. We just have a project where they say, oh, we want to connect the 100 most important databases for us. We want to explore how semantic technologies can help us to be able to scale this and not getting stuck in saying, okay, we want just to link these two databases, which have a similar scope, but we want to link across the enterprise, across domains. And there you need flexible models, and the data is really in a graph-like structure. So SmartLabs in the future will provide the enterprise with integrated data that is based on common reference data and structured vocabularies. It is easier to share data. You use the technology that is there, scalable, and you need to think of your data in terms of conceptual representations. What does an experiment look like for you? Don't let the application manager just decide, okay, I name this property here that way, and I name it this way. Look at the data more from the strategic perspective. And then the data scientists don't have to work in the data swamp to clean up the data. Thank you.